Hello everyone, welcome back to CP Part 2 Purple. In the previous videos, we have talked about time complexity, we've solved a lot of problems, we've had a first contest, and today we'll talk about some of the most important topics in competitive programming. You will encounter these topics in almost every question you solve. You gotta think about them, you'll have to optimize them, so let's dive into it. First, we'll talk about brute force. What is brute force? Brute force typically means going through all possible solutions of my problem and picking the best one for me, the most suitable one for me, and what my question requirements are. It's the most fundamental problem in this competitive programming because it's the simplest way. Like, I just iterate through all of the solutions and pick the best one. It generally gives us the correct solution, but most of the time it will give you a time error. It's most suitable for solutions which have low input values, but in most of the problems you will have to think about it. Brute force solutions are further needed to be optimized to give us the perfect solution, and let's see how it typically works, how we will encounter problems. But let's note down some points. Too slow for most problems. I'll mention it again, even though it is slow, most of the problem solving will happen using brute force. Your idea how you're gonna solve it, the first thought that comes to that you need to think about while solving a problem is, without any optimization, how will I solve it? How will I think of approaching the problem? And that's where brute force comes in. It helps you further solve the problem in a much quicker way. We'll solve a few problems to analyze how brute force works. So let's see. Our first thing that we'll talk about is generating all possible subsets of a set. So for those who don't know what is a subset, before that let's talk about what is a set. Set is a group of distinct characters or numbers. That's it. Example. Let's take an example for this question. This is a set. Yes. As you can see, all the numbers inside them are unique. None of the characters or numbers are repeating. So this is a set. Now what do I mean by all subsets? Any set that can be formed using characters inside us from this set is called its subset. Now I'll write down all the subsets of this set so everyone understands. There will be a null set, no values. There will be 0, 1, 2, a 0, 1, a 1, 2, a 0, 2, and 0, 1, 2. Like, can't forget itself. As we can see, the count of total number of subsets is 8, which is 2 raised to 3. So this gives us a formula. It's a normal formula, everyone knows it. The total number of subsets from a given set is always 2 raised to n, where n is the size of the set, the origin set. 2 raised to n. Set, and this is total number of subsets. Let's highlight it. Now how do I solve this? How do I get total number of subsets, all subsets from a given set? There are two ways to solve this. Both are brute force methods. Like there is no improved solution for this, and the time complexity will be 2:1. I know it's quite slow, but no optimal solution has been found for this particular problem till now. So first method will be recursive method. Here we'll use a recursive function and we're gonna solve this. The second method will be a bit manipulation. In this method, we typically use represent a set as a series of bits and get all possible sets, all possible binaries till 2:n and get the values. Like we won't solve this today as we've not talked about bit much, so we'll cover it in further classes, but today let's solve the recursive one. I'll write the code first and then explain it. Of course, I'll explain it in between also, but let's just move in a way. Let's assume a subset. Let's create a vector int which will be called subset. This will contain each subset that will output, and the size of our size of our origin set is 3. Let's assume it's just 0, 1, 2 for convenience. Like assume that it's already assigned. Other than that, we can connect it. We can use a vector or a set with k as its indicator. But let's just for convenience assume this is our set and proceed. This will be the input as where it's starting. If this cout doesn't work like that, I've just written it like this so for convenience. This is a pseudocode. What is a pseudocode? Pseudocodes are codes which are written to understand how our logic works. Like you can write this code in any language, suppose you're doing C++, Python or whatever, but you need to understand how it actually works, the idea of what my code will be doing, what each line is doing. So this is that. Here if n is equal to k, like the input in our search will be equal to the size of the subset, total size of a set, then it will output the subset. This temporary subset which will be called is created here. This is subset. Oh, sorry, I'll write it better. Let's just, yeah, I've used K here. Let's solve N. Yeah, this works. This is our pseudocode. Here we have created a subset, and with we've told it that the size of our set is 3. We have initialized subset 2012. Like, it can be anything. Actually, we need to know how do we solve this question. We have created a search function int n of where n is, we'll state that whenever n is equal to k, like, let's just solve it. Let's go through it and I'll show how it works. If n is equal to k, like if our input is going to be the size of the set, then it will output whatever the subset is there. Else it will call itself again with n plus 1, which will be initial size plus 1, initial input plus 1, and go through. If it will push back n, and I think the code seems logical. This popback function is quite important here because the subset is outside the function search function. As this subset is outside the search function, it won't refresh itself with each iteration. हर बार ये सर्च फंक्शन कॉल होने पे सबसेट फिर से नल वैल्यू पे नहीं जाएगा, फिर से रिफ्रेश नहीं होगा, सबसेट की वैल्यू वही रहने वाली है. इसलिए this pop back function is very important. I think pushback and popback everyone knows, else I'll explain. Pushback means we are putting the value in the subset, and popback means we are popping the value from the subset. That's it. Popping the last value and pushing the last value in the back of the grid. So how do we solve it? We'll solve it using calling search of 0, and it will output it. How does it work? Let's see. Suppose, let's take this example. Here I've called 0. Search mein, in search I've called 0. Search goes 0. 0 checks if it's equal to k. 0 is not equal to 3. It moves further. It calls itself 0 plus 1. 1. It calls itself, where search will call a 1. Then assume that it's here, this is a function. This is search of, I'll write it in the top and you can further cause search of 0. Yeah. These are all function calls. Again, 1 is not equal to 3. It will move further. It will call search of 2. 2 is not equal to 3. It will call search of 3. Now 3 is equal to 3, and currently our subset comprises of nothing. There's nothing in there. Here it calls 3, and at 3 it will output. It won't go to the else function, it will output. And as it's nothing, 3 will output us a null set. Here, as it will go back to its above branch, 3 will go back to 2. Search subset dot pushback 2. In this function, this 2 will push back 2, and it will again call a 3. This 3 will again output a subset. But here, as here the subset currently contains 2 in it. So this will output 2. This 2 is popped back. I'll construct the entire tree for you guys. This will go back to 2 with 1. Now this will be I'm writing subsets with this sign, so it's 1 2, as now this 2 also goes back to 1 where it was called. Subset dot pushback 0. Now the whole tree will be repeated here with 0 in it. It's just getting repeated because here it's the same search function is being implemented with 0 initially pushed back. As you can see, it started with null set and 2 set and another value 2. Then it went back up and it pushed a 1 inside the set. So these both values had a 1 with them. Null set and 1 set will gives you a 1 as subset, and this one gave you us 1 and 2. Cause this entire search function is getting repeated after a pushback. As it goes behind it, this one will get popped back, and here it got added a 0 here, and this was the entire branch, the entire this tree was repeated. I'll use a different color. So this entire this entire side was repeated on the other side with just 1 in it, 0 in it, sorry. So next let's talk about backtracking. Backtracking is also one more way in brute force. It's one of the optimization methods because we saw the time complexity of this problem. Let's calculate the time. The time complexity of this problem is two raised to n is too much. You won't be able to last anywhere with 2 raised to n. So, but we can't help ourselves in this question, but further questions we can. Backtracking is also a form of recursive method. In this, whenever we see that we are not able to move to a solution, we eliminate that branch completely. For backtracking, we'll look at a peculiar problem, which is n queens problem. Here we build solution one at a time. And eliminate any invalid state. What is an n queen problem? Like, it's a chess problem where you have to arrange n queens on a n cross n chess board such that no 2 queens attack each other. For simplification, we'll consider only a 4 cross 4 chess board. So in this chessboard, we have to arrange 4 queens such that no 2 queens attack each other. What's the idea? How do we do it? So anyone who has not played chess, let me tell you, a queen can attack anyone on the diagonal or anyone on its particular row or column. Yeah. So first thought that we'll see is if it can attack anyone on the row column, on each row or column, there will be only one queen. We get the idea. If I put a queen here, so this row is gone and this row is gone. Then I only have these squares. So how do I solve this? For everyone to understand, let me give you a configuration of where we can put the queens. General configuration, like a solution of what you can actually, how you can arrange the queens by. Yeah. Now this is a solution where I have placed 4 queens in this 4x4 board and none of the queens attack each other. Let's take one queen at a time. This queen eliminates this diagonal, and this. No one's there. And this diagonal. Queens also attack on the diagonals. So this is safe. On the this queen attacks this diagonal, this one, this, and this. We can see the first queen is safe and none of the queen is attacked. For the second queen, this one's attacked, this is attacked, these 2 rows are attacked, and these 3 are attacked. Again, none of the queens are hit. Similarly, you can check for other 2 also, and none of the queens are attacked. I'll write the code for this, and again assume that this is a pseudocode and this is not an actual code. Let's just draw the diagram for this one here. We'll write the code later. Let's draw the diagram first today. This is our initial chessboard of 4x4. When we start a loop, what are the possible values that we have? Let's do a brute force and let's see what are the possible values that we have. If I'm placing the queen on first row, I'll have 4 options. I can do it so yeah, these are all 4x4 chessboards, and the 4 options, when I put it in the first is I can put it here, I can put it here, I can put it here, and I can put it in the last column, anywhere in the 4. When we proceed with the brute force, we take all the possible paths. So let's take this branch. After putting my queen here, in the second row, what are the possible places that I can put my queen? we know there's a queen here. Other than that, we can put it here, 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 oh, sorry, here, or here. Now, before proceeding for further branches, let's just check, is this a valid position? As we can see, these queens are attacking each other, so wrong. These queens are attacking each other, wrong. These queens are attacking each other, wrong. This one's valid. So with backtracking, we will not proceed for any of these branches. We'll check on each iteration whether the preceding branch is correct or not. If it's not correct, then we'll prune these branches or we'll cut off them. We'll not proceed with them. For the further solutions, for the further code, we'll only proceed with this branch. Now, rather than generating each again for this, it's quite useless because these are already invalidated. So further checking will only be done for this branch, and again it will be gone back. This will be done for all four. In this way, we optimize our brute force, and this gives us a much better solution with a much better time complexity than other codes. Yeah. Another problem we'll talk about is, this is the last problem of backtracking, is finding a path. Like, suppose I have a 7x7 grid. Yeah, today we are in the grid a lot. So now here in the queen search problem, we took a 4x4 grid, so it was convenient for us. This can be done for any size of grid, and the code is quite simpler. We take a double for loop, and we use a recursion function, sorry, and after each queen place, after each time we position a queen, we check if it's hitting any other queen or not. If it's hitting another queen, then if by hitting another queen, we just check if there's a queen on its diagonal, if there's a concurrent queen on its diagonal, or any of the row or column. If yes, then we invalidate that branch and kill it. Otherwise, we further proceed down. Third question is finding all possible paths. Suppose you are given a grid of size n. Let's take 7 this time, because 4 is quite small for this question. So I want to explain how large this grid can get. So now we're gonna see how bad brute force actually is. Why it might take a lot of time using brute force, and how we can further optimize using brute force to solve our competitive programming questions. Any question on code forces, lead code, first thought you're like, yeah, let's just go through all the solutions. Then you need to think how we can further optimize the solution. 6, 7, 1, 2, 3. Now assume this is a maze and there's an opening here and there's an exit here. You can enter from here and you can exit here. From any box, I can move to other box which is connected to it, left, right, top or bottom, not diagonally. So how many ways are there such that I can go from this particular box to here? Quite a lot. And how do we solve this question? with basic algorithm we can think. I'll tell you the solution. If we just do a proper brute force, it will take us 76 billion calls, and which will take us 483 seconds. This is in C++ to just solve this question. Just solve this question. Now, anything. How can we optimize this? Let's look at this grid. As suppose we are moving from here. If we are at the first path, there are two options for me. I can move here or I can move there. Right? Left or right. And if we rotate this grid, I don't know if we have an option here. Like, if we rotate it here, we can, even after rotating, like just rotate your phones, you can see left and right are symmetrical. The grid is symmetrical. Like if I move here and here, and if I move here and here, both are quite symmetrical. Like if I can move from a path from this side, then I can move from a path from that side too, using the same path. Just top ka right kar do. Let me show you. Okay, one thing I need to mention here, just such that all squares, पहले तो चेक होता है कि विजिटेड है कि नहीं है, इसीलिए suppose I move from here, 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 here. Now suppose this is my path, I went straight. Now do I need to check it for right one also? Cause I know it will work for right one, cause these both are symmetrical. This works for this top and right also. So we can half our searches using this. Like we can make it 2 times faster. We just need to calculate all the paths starting from down below, and we can multiply it by 2. So our code just goes twice faster. Now this cut downs to, I don't know. Let's just take this 244 seconds around. 242 seconds. Further, what can we do? Suppose we have not visited all these squares. Like there are total 49 squares. If the count of number of squares visited is less than 49, suppose 29, and I've already visited the square. After visiting the square, I can't visit the square again. Then if at my 29th position, this is my 29th square visited, then I can't visit this square again, and I can't exit with visiting all the squares. Then that's an error too. So we again backtrack, we prune the search. This further reduces, like it's all calculated, so it further reduces our path to 119 seconds. Using just this much optimization can reduce your searches by this much. One more thing that we have not hit, one more thing we can think about. Let's go. There's one more thing that we can think about. Yeah, I'll show it to you. Let me draw the tree. Draw it again. if we go from here and here, now currently, like suppose this was my path, I went from top to bottom and anyway like this, it can be like this, or suppose I, and or it can be like this. I'm at this box. Now at this position I only have two options, whether I move left, whether I move in one direction or another, and anyhow I won't be able to visit both the paths. If suppose I move above, I won't be able to visit the boxes below, and similarly if I move it down, I won't be able to visit the boxes above. This further reduces my problem and I can again backtrack. Initially, which was impossible to even solve 109, I mean, it was not impossible, but 119 seconds is too much. This single optimization reduces these 119 seconds to 1.8 seconds. These are all C++ times, so Python developers, please. With no, this the motive of this was just to show how much brute force is important and how we can further reduce it, how further optimizations reduce the solutions. With further much optimization, this question can be solved in 0.6 seconds. We'll place this question probably in the upcoming text, like I don't know, but yeah, this was brute force. Thank you. Next thing that we'll talk about is greedy algorithm. So what is greedy algorithm? Like greedy algorithm constructs a solution like piece by piece. It will look at my solution. Just it will at each step it will check which solution is best and for according to the problem, and it will accumulate it and hopefully it will hope that it's the best solution. Like yeah, this algorithm really works on intuition that it's the correct solution. Unlike brute force, this solution can get wrong sometimes. Greedy algorithm is not always the perfect solution, but it is quite fast and yeah, works most of the times. Fast. Mostly this doesn't reconsider its choices. Like once a decision has been made, once it's decided that this is a solution, it doesn't go back and check whether it's correct or not if more values are added. So that's greedy. The perfect way to depict a greedy algorithm and how it can go wrong a lot of times is the coin problem. Let's take an example. If I have a set of coins 1, 2, 5, 10, 100, 200, 20, 50, like Yeah, these are my coins and I need to get 520 rupees, and I only have these notes. I have 1 rupee note, 2 rupee note, 5, 10, 100, 200, 20, 50. So what algorithm can you think of so that I need to use least amount of notes? If we use greedy algorithm, I'll tell you the solution. We'll look at this, we'll sort it in ascending order, descending order, 200, 100, 50, 20, 10, 5, 2, 1. Then I'll check if the highest rupee note is being used here. If it's okay to be used here, then I'll subtract it and add a note, else we'll go to the next one. Here we'll check for 200 first. Yeah, 200 rupee note can be used. Now I need 320 more. Again and I've got one note of 200. Again I'll use a 200, 120 more. Two notes, 200. Now 200 doesn't work. We'll proceed to 100. Does 100 work? Yes. Now I need 20 rupees more. I have two notes of 200, one note of 100. Now 50 doesn't work, 20 works. I don't need any money more. Two notes of 200, one note of 100, and another note of 20 rupees. So as we saw, we took a greedy algorithm here. At each time we checked if the highest value, we compared that if 200 is more than or less than the amount of money required. If it's less than the amount of money required, we subtracted it from the money and added number of notes by 1. We did this till we were left with no money required, and it worked. But greedy algorithm isn't the best algorithm most of the time. Another example that we can show is where greedy algorithm fails. Just to tell you, greedy is not always the best solution. If I need 6 rupees and I have coins of 1 rupee, 2 rupee and 1 rupee, 3 rupee, just 3 rupee and 4 rupee. So what does the greedy algorithm tell us to do? First we'll check if it's, as 4 is the largest, first we'll check if it's more than 4. Yes, it's more than 4. Then I need 2 more rupees. I have a note of 4 rupee. Then we'll check if it's more than 4. No, it's not more than 4. We'll check if it's more than 3. No, it's not more than 3. It's more than 1. So now I need 1 rupee. I have one note of 4 rupee and one note of 1 rupee. Now I need one more rupee. So again, I need no money. One note of 4 rupee and two notes of 1 rupee. This gives us further 3 notes. Okay, these are small numbers, so let's consider coins. It's funny calling them notes, but let's call them notes still. But is this really the best solution? No, it's not. Let's consider taking a 3 rupee note here. If at 6 rupees I used a 3 rupee note twice, I would have gotten the solution with just 2 notes rather than 3 notes which my greedy algorithm suggested. So this shows us that greedy algorithm is not the perfect algorithm most of the times, but it's still quite useful in many of these questions and solutions. So we'll consider these questions for now. This coin solving problem would have been done using dynamic programming, which we'll further encounter today. So yep, let's further proceed. One question that we'll encounter for greedy algorithm is event scheduling problem. uh, Event first is coin. Guys, today I've only considered pseudocode, as we'll be disclosing contest solutions editorial. So coding part is covered in the editorial videos. We will try to discuss most of the problems. So to cover most problems, we are using pseudocode method here. This is event scheduling problem. Suppose I have 4 events with each start and end time. Now my job is I want to attend maximum number of events such that none of the events overlap. I need to attend majority of the events, so none of the events overlap. How do I solve it? Like, one thing that we can think of is, let's attend the shortest event, the event with which has the least duration. Let's just attend that. So least amount of time is spent in events, and so we can attend more events. Like A takes only 2 minutes, so let's just attend A first. The event with which takes the least amount of time, let's just attend that event first. Another strategy that we can think is, let's choose the event that starts the earliest. The event that starts the earliest will be, I'll be attend most events. If it starts early, then I'll always be in an event maybe. Another thing that we can think of is, let's attend the event that ends earliest. The event that ends early will give me much more time, because if the event ends early, then it will start early too. It kind of considers the second idea too, and it will, and as it will end before other events, I'll obviously have option to attend remaining events too. So let's try checking for each of the 3 strategies. Suppose I chose the event which will take me least amount of time. With strategy 1, strategy 2, here we can see each of the strategy will give us 2 events. Like in strategy 1, I'll attend event A and then I'll attend event D. In strategy 2, I'll attend event A, then I'll go to event C, and in strategy 3, I'll attend event A, then I'll go to event D. But if the problem was much more complex, which strategy do you think will be the best? I know event strategy 1 doesn't work. Suppose the event which has the shortest time is at the starts in after all the events end, then strategy 1 doesn't work. Like, suppose this was 7 and 8, then strategy 1 would have asked me to just attend event D, and it fails for everything. So strategy 1 doesn't work. Strategy 2, it might seem like a good idea, but it's also not a good idea. Suppose the event A, that it tells us that attend the event that starts the earliest. If we attend that and this ends at 12, we are stuck for the entire duration of a single event, and because of this we are not able to attend any other event. Now again our count goes on, and strategy 2 is also not that optimal. Strategy 3 kind of ensures that if it's ending early, then it's obviously starting early too. So anyhow, strategy 3 will be our most important strategy in these kind of questions. Another question that we'll solve is, so okay, now let's move on to dynamic programming of how actually do we solve the coin problem. How do we get an optimal solution? But before that, let's take a look at we can say an application of greedy algorithm. It's called Huffman encoding. It is used sometimes in competitive programming, like not much, but it's just something that we thought of covering. Like it's a type of encoding that uses greedy algorithm, and it's like done to characters or series numbers, any code word or any word where like yeah, suppose you are given a string. The main idea of Huffman coding is like the one which has most occurrence. It should be reduced to, like, it should appear lesser number of times. So like I'll show you an example. Suppose we have a string A B, example there. Let's take this string. So here we can see A appears 5 times, B appears 1, D appears 1 time, and C appears twice. So in this kind of algorithm, we pair up the ones which are smaller in number. This is like used so that such a long string takes up lesser space and it's encoded into binary. Cause in that any kind of number is encoded into binary. Like the most occurrence, it's to reduce the size. So how do we solve it? Like how do we get the Huffman encoding? Initially we take our nodes, A which is 5, B which is 1, C which is 2, and D which is 1. Now we can see B and D, which are the smallest in number, they pair up. We arrange it in descending order, and the ones with smallest number will pair up. So A comma 5, C comma 2, B comma 1, and D comma 1. These are smallest in number, so they pair up. Now this will go to BD 2. Their weights will B comma D and 2. Their weights align up. Now again we do the same thing. It will be C and B, as these are the smallest one. B comma D comma C. Now this equals 4. Now this will then pair up with A, which will be B comma C, B comma D, comma C, comma A, and the total weight will be 5 plus 4, 9. Now let's start from the top. Just like if we make this in a physical way. Let's arrange it. This left node will give us a 0 and right node will always give us a 1. Now this gives us 2. Again left node gives us a 0, right node gives us a 1. This gives us 4. We'll again, as both the weights are equal, we don't need to arrange it again and again. Now in the final one, this first needs to be arranged. So it will be B, D, and again left one gives us a 0 and right one gives us a 1. As you can see, we don't need to arrange it again and again, as even after adding it's in decreasing order, else we'd have to arrange it. So it's like A will be written as 0, C will be indicated as 0, 1, one 0, sorry. P will be indicated as 1, 1, 0. See, we move above, we move to the top from the tree. It goes here, 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 and D will be indicated as 1, 1, 1. So this is Huffman encoding. I think we've covered everything in greedy algorithms now. Again, I'll repeat the Huffman encoding. Like, we take the strings, we count the number of characters, we arrange them in decreasing order on each iteration. Here we have not done it on each iteration as it was already in decreasing order. Then after we create trees. After on each iteration we create trees. We give the left one as 0 and right one as 1, and we pair them up till all the values are met. So the largest ones are depicted with smallest values and smallest ones are depicted with larger values. And this is how we encoded A, B, C, D, the string. Now let's move forward to dynamic programming. What is dynamic programming? Now this is the most important part. I'll particularly say this will help you solve competitive problems in contests. This combines complete search, which is mostly correct but slow, and greedy algorithms, which are fast but they are sometimes wrong, like a lot of times quite wrong. How do we code correctly and efficiently? This is where it comes in. So in dynamic programming, there's a very particular concept, memoization. Like every time we solve something, we memorize it. Anytime a question is, we found a value, we memorize it in our memory, we store it in our memory so that we don't need to call the tree again and again. It works in a peculiar concept, like we break the larger problem into smaller sub problems and we solve each sub problem, save the result in our memory so that whenever we need the result again, we'll call the initial value. For example, let's take let's just do the coin search, the coin problem. Okay, so let's solve the coin problem. This is the question. Like we've got 3 coins, 1 rupee coin, 3 rupee coin, and 4 rupee coin, and our aim is to get a 10 rupees in minimum number of coins. So let's solve it using dynamic programming. In dynamic programming, the most important thing is to break this down into sub problems. Like we'll use recursion here. So what's the most simplest thing that we can do? Create a function. Let's just create a function, call it solve, and assume that this gives us minimum coins to get x. Okay, let's just assume if we use solve of x equal to, we want to find solve of 10, right? Now what if we have solve of 0? Solve of 0, this will be 0, as we don't need any money and solve the 0 can be given as 0. Now for solve of, suppose x, if the last coin taken was a 1 rupee coin, so solve of x, if the last coin is a 1 rupee coin, then won't it be like solve of x minus 1 plus 1? Cause अगर मैंने solve से 1 रुपया ले ली, if I've taken 1 rupee from solve and in the best most optimal solution there's a 1 rupee coin used, then it will be like 1 coin added and 1 rupee reduced from solve, so that this gives us the best. And if the smallest coin taken was the 3 rupee coin, assuming, then solve of x can be given using solve x minus 3 plus 1. Similarly, solve of x can also be given as solve of x minus 4 plus 1. Assuming which one is optimal, we don't know. Assuming any of them could be optimal. So solve of x can be given as minimum of x minus 1 plus 1 comma solve of x minus 3 plus 1 comma solve of x minus 4 plus 1. In all the three scenarios, cause we just checked the ingredient, it's not going to be always the highest number, the largest number. It can be anything. The smallest coin taken can be anything depending on the question, just to get the minimum number of coins. So solve of x can be, we can take a coin from any of the 3 values. We just need to check which will give us the minimum number of coins. So this is the first step. Let's now think of it like it can be anything. Suppose I'll give the solution. The solution is 4 plus 3 plus 3. Like 3 coins for 10. Now here let's see how it will work, how the recursion will work here. If we call solve, it will check for solve of 9. of x equals minimum, solve of 10 if there was 10, solve of 9 plus 1, comma solve 7 plus 1, comma solve 6 plus 1. Now here, if we go into each of the solves separately, now solve of 9 will also give plus 1, comma solve of 6 plus 1, comma solve 5 plus 1. As we can see, this here there's a solve of 6 and here also there's a solve of 6. Rather than finding the solve of 6 again and again and again and going through the entire loop again and again, maybe in one of the iterations here we'll find the solve of 6, store it in an array, suppose store it in a vector int coins, which will be for 6 equal to solve of 6, and whenever if coins box 6 exists, if this value is like we have filled this value, we'll check and we'll keep a check if we have filled this value, then it can directly ask this rather than solving it again and again, rather than going through the recursion again and again. This saves our time from 2 raised to n to much and quite a lot less. I mean, I hope everyone understands it. So this way we can do any kind of counting solution. Let's take another example, like if n equals 5, then our coins will be 1 plus 1 plus 3 or 1 plus 4. We need this solution rather than this, and our dynamic programming ensures we get the best solution. So today we have finished with greedy algorithms, dynamic programming, and brute force. These are the most important pillars of competitive programming. Hopefully everyone enjoyed it. Thank you.